Okay, welcome everyone. All right, so this is our third class on 295B. We'll be putting up a problem set later today. Not quite sure exactly when it'll be due, uh, depending on when the section is scheduled. So you'll have about a week or maybe a week and a half probably to do it. And these are basically standard problems from the textbook from chapter 1. Just give you some practice in the second quantization method if you haven't seen it before. Yeah, so the book, well, I mean, officially I recommend that you buy it, but I understand it's also available online. I'm not going to give you the link, but I imagine you can find it. But we'll try to put at least the problem. I mean, the problems will refer to material in the book, but we'll explicitly write out the problems in there. And if you need a copy of certain pages in the book, I think I'm willing to make a few copies at home and email them to you, just a few selected pages. Okay. Any questions or comments? Oh, right. I have to now connect up with my screen. Okay, so we're now talking about Hartree-Fock theory. So I'm just going to finish the basic setup, and then we'll apply it and do a calculation of the basic properties of electrons in metals. All right, so at its heart, the Hartree-Fock theory is just a variational calculation where you have some many particle system with some interaction between the particles, V, and you can also imagine some external potential U. So typically in condensed matter atomic physics, the external potential is from nuclei, which are assumed to be stationary. And in a crystal, this would be some kind of periodic potential. And this will be just the ordinary Coulomb potential, depending on the spatial separation of the electrons, if you're referring to electrons. Okay, so the basic idea is you choose a function, many-body wave function. And so you choose a wave function, which is just a Slater determinant of some single particle states phi alpha of R. And in the second quantized form, the state is just written this way. You start with a vacuum and you add particles in the state alpha by the creation operators. Now, this is not to say that the actual wave function of the system is of this form, but this is a guess. So this is an approximation. Up until now, when we went from first quantized to second quantized representations, it was all exact. It was all exact, even though the actual wave function may not be a Slater determinant. What is true is that the wave function is a linear combination of Slater determinants. And that's really all you need for the setup of the second quantized formulation. So now we are making a further step. We are not assuming it's a linear combination of Slater determinant. We are assuming it's just one Slater determinant. So the basic idea, excuse me, is to just optimize this Slater determinant, and you optimize it by choosing these functions. So you have n wave functions to choose, and you're going to choose the best wave function which optimize the energy of the many body state. So, a first guess for the wave functions would be just the eigenstate of the one particle Hamiltonian, this one and this one. But that, you could start with that, but that's not where you'll end up typically. You could end up with different wave functions which optimize the many body energy than those that optimize the single body energy. Okay, so you evaluate the expectation value, you get some functional, you take the variational derivative of the functional, and you get a Schrodinger looking like equation with a non-local potential. And the new twist, of course, is that the potentials themselves depend upon the wave functions. So you solve it by a method of iteration. Okay, so that's the basic procedure, and some ridiculous fraction of papers in Physical Review B are, when you think about it, implementation of solution of these equations in many different contexts. But even as written there, this is quite complicated. So we simplify things by setting things up in the Hartree-Fock formalism, in the operator formalism, sorry. So now I'm going to present the algorithm, which is the one we're typically going to use in this course. We're using the second Quaiders formulation. We're going to derive the Hartree-Fock equations. And in this approach, we think of the Hartree-Fock equation somewhat differently. We think of it as a mean field theory. Now, mean field theories have a long history in physics. They go back to really the van der Waals theory of the interacting dilute gas, and that led to the critical point between the gas and the liquid in carbon dioxide and so on. And then furthermore, there was the mean field theory, the Curie-Weiss mean field theory of magnetism. And we're also going to see that a little more explicitly in the next chapter. And the basic idea of all these approaches, the Hartree-Fock approach, the Curie-Weiss mean field theory, or the van der Waals theory, is that you have some interacting many particle system, and you try to write down some Hamiltonian that only acts on one particle. So in this case, our Hamiltonian that only acts on our favored particle will be this Hartree-Fock Hamiltonian. So it's a one-body Hamiltonian. It's only going to pick out and act on one particle. Then what do you do with all the other particles? Well, basically, you take all the other particles and replace them by some average over the configuration of the full system. That's what in van der Waals theory, you replace the volume, excluded volume, by the average volume of all the other particles, and the pressure by the average pressure of the other ones, and so on. And in Curie-Weiss mean field theory, you replace the magnetic moment of the other particles by the average. So here, in the same vein, you're going to take this two-particle term here and replace it by one-particle term by replacing the other terms by averages. So the twist here, this is a quantum system. And there's many different ways of taking averages, and the rule here is you just take all possible ways. So you average C dagger with F, C dagger with E, and so on. And then because these are fermions, you pick up a minus sign every time you move an operator through another operator. So in this case, why is there a minus sign here? Well, you imagine you want to move the E next to the C, and you have to move it through the D. And so there's only one change, and so there's a minus sign. Whereas, why is there a plus sign here? You have to move the F next to the C, and that moves through two fermions, and that gives you a plus sign. Okay. So you can just view this as some, heuristic guess, just like the Curie-Weiss mean field theory or the van der Waals theory was a guess. But it's better than that. It's also a variational estimate. And you can show that the equations you get this way are the same as the equation in the previous that I just showed you. I won't, okay, that's written up in the books, and it's not that hard to see after you put all the indices back in. Okay, so now you have some one particle Hamiltonian, you diagonalize it, you find its eigenfunctions. And this kind of step you're going to look at in one of the homework problems, and you get some eigenenergies, E alpha. So now you've got the one particle energies, and you've got the one particle wave functions, which are the states phi alpha, which are eigenstates of the Hartree-Fock Hamiltonian. And so you're going to build up a many particle state. So here we're thinking of the grand canonical ensemble, where there's a chemical potential. And in the grand canonical ensemble at zero temperature, you just fill up all the negative energy states. So you just fill up all the states with epsilon alpha less than 0, where epsilon includes the chemical potential. Okay, so that's step A. That's where we were last time. And then what do? Now you have the wave functions and the energies. but these depend upon these expectation values. So you recompute the expectation values, and then you go back and keep iterating until the thing converges. Okay. All right. So now, then what is the ground state energy? Okay, the ground state energy is the expectation of the original Hamiltonian. So there are two different Hamiltonians you have to keep in mind. There's the full interacting Hamiltonian, and there's the Hartree-Fock Hamiltonian. The Hartree-Fock wave functions and the Hartree-Fock state, this is the Hartree-Fock state, only depend on the Hartree-Fock Hamiltonian. So the Hartree-Fock state is an exact eigenstate of the Hartree-Fock Hamiltonian. But we're going to take the Hartree-Fock state as a variational eigenstate of the true Hamiltonian. Okay, we're not really interested in the Hartree-Fock Hamiltonian other than it gives us the Hartree-Fock state. Okay, it's the exact eigenstate of HHF. So what is the energy of the true Hamiltonian? Well, the energy of the true Hamiltonian is not the energy of psi Hartree-Fock under H Hartree-Fock. The energy of psi Hartree-Fock under H Hartree-Fock would be just the sum of all the eigenenergies. And that is not correct. And the reason it's not correct is the following. So let's take the wave function, our variational wave function, and the energy of the full Hamiltonian. And we want to evaluate this expectation value. So we go ahead and just evaluate the expectation value by the same rule of just factorizing everything. So if you factorize it, of course, this A dagger B is as usual. But now, when you look at this term, there's only two different ways of factorizing this. You can pair a C dagger with E, and then you have to pair a D dagger with F. They both have expectation values. So this is, this is the actual energy, expectation of the energy that you're interested in. But is this sum on E alpha? Answer is not. I mean, you know what E alpha is. E alpha is just the expectation value of this. So if you just look at E alpha in the alpha state, that's the expectation value of A dagger B. And then you sum over all of them, you will indeed get this term. Then if you take a look at the expectation of E alpha in the alpha state, you will get C dagger F times expectation value of D dagger E. But you'll also get that term again here. So you'll get this time this expectation value and this time this expectation value, which are the same. And so you'll get this term twice. So that's the problem. You're getting this term twice and you're getting this term twice. So you have to subtract that out. So that's the rule, that the actual energy of the system is the sum of the Hartree-Fock energies minus these expectation values. So there's this correction term that you have to put in, which sometimes people forget. Okay, so really another, just a simple way to say it is, when you have some in fact, sometimes it's useful to just keep track of this right at the very beginning. So if you have some operator A dagger B, C dagger D, well, if you replace it by expectation value of A dagger B, C dagger D, plus, I didn't normal order it, but excuse me, plus A dagger D. No, let me do it correctly because there are some subtleties here. So it's A dagger C times B dagger, oops, sorry. Sorry about that. A dagger C, B dagger D, minus the same thing again, but with the expectation value on the other term. So you just keep in mind that you have to correct that by saying that you just replace this, but you also have this term here. Okay, so this is just a constant as far as the Hartree-Fock Hamiltonian is concerned, so you don't really worry about it, but you have to keep track of it if you're actually interested in the total energy. Okay. All right. So in fact, you can think of this as a much simpler variational problem too. In the end, what you notice is that the Hartree-Fock Hamiltonian doesn't really depend on the full wave functions. You don't really need the full wave functions. What you need are these expectation values. So the whole thing is actually a lot simpler. These are some numbers. There's just some set of numbers. So we can think of these numbers as some free parameters, and you're going to minimize the energy with respect to those numbers, because these numbers depend on the Hartree-Fock Hamiltonian, and therefore they depend on the Hartree-Fock wave function, but we're not really varying the full wave function. We don't need the full information of the wave function to work everything out. So you can even view this as a problem as stated here. This is what you do. There's an algorithm that I've written down. That is, you minimize this expression here. So what you do now is you pick some numbers. You find the Hartree-Fock Hamiltonian based on those numbers. Then once you have the Hartree-Fock Hamiltonian, you can compute this expression. And then you just minimize this. You can also do it that way. And you get the same answer where these things are self-consistently determined at the minimum. These quantities will then become equal to the expectation value of those numbers in the Hartree-Fock Hamiltonian. All right. Okay. And then another interesting thing is, what are these E alphas? So the E alphas are not just simply related to the ground state energy, as you've seen here. There's a correction. But they are simply give you something very interesting. And what they give you is what we call the quasi-particle energies. So the eigenvalues of the Hartree-Fock Hamiltonian, which is a single particle Hamiltonian, are the energies of the quasi-particles. And what is that? So that here's one way to define it. You take the Hartree-Fock Hamiltonian, that gives you a Hartree-Fock ground state, and then you add another particle to it. So this particle obviously will have to be in a state that's not already occupied. So you add an extra particle above the Fermi sea. And you look at the expectation value of this new wave function with n+1 particles with respect to the wave function with n particles. And then you can show by just manipulating in exactly the same way that this is exactly E alpha. So what the eigenfunctions of the Hartree-Fock Hamiltonian are the quasi-particle energies, which is the energy in the grand canonical ensemble to add a particle. And similarly, you can show that it's also the energy to remove a particle. Minus E alpha would be the energy to remove a particle that's already occupied. Okay, and that statement is sometimes called Koopman's theorem. Koopman was a physicist who then became an economist, and I think won a Nobel Prize in economics. Well, okay, but he's got this name attached to this important interpretation of what these eigenstates of the Hartree-Fock Hamiltonian are. All right, any questions?
Yeah, can I ask a clarification question?
Sure.
On the original Hamiltonian, actually, the A dagger B plus C
Yes.
dagger D dagger. So I, understand like in terms of, like in a diagram picture, the second term there, the C dagger, D dagger, E, F, like two separate particles coming in, two particles out.
Yeah.
What's the interpretation of A dagger B? And I guess specifically I'm confused, why isn't it just A dagger A? Like why are A and B different operators?
Well, just because we work in a basis in which which is not the eigenbasis of the one particle term. I mean, so what you're saying would be true. So here, suppose I take this Hamiltonian here, the A dagger B term represent the contribution of this term and this term. Okay. So that's the one particle term. All right. Now I have some, let me write it out here. So what would I do? So literally this is what I'm doing. So I have my one particle term, which is minus 8 bar squared over 2m grad squared plus some u of r. So I'm only picking out, I focus, it's a one particle term, so I don't put a sum over particles. All right. So this I can find its eigenfunctions. So I've looked for the eigenfunctions of H1, phi alpha, and this would be E alpha, phi alpha. Okay. So associated with this eigenfunction, there's a creation operator C dagger alpha. So now you're correct in this basis. H1 would be E alpha sum on alpha in this in the second quantized form, C dagger alpha, C alpha. Okay, so this is what you would do if all you were interested in solving for the many particle problem, the single particle problem. But in general, you could pick some other basis. So if I just suppose I had another basis, you know, psi alpha. So I had another basis of states phi, let me call them psi alpha. So these are some other wave functions. So then what is my H1 in this basis? Well, my H1 in this basis, so let me call this H1 0 because it's a single particle. H1 0. This is the full many particle Hamiltonian. So the H1 in this basis would be something like this: sum on alpha beta psi dagger beta, the matrix element between psi beta, or let me call it C. So there's a creation operator in the psi basis, which I'm still calling with the same. Okay, let me use a different index. That will make it clear. So this is some other basis, psi I. So there are operators Ci that create and annihilate in that basis. So C dagger I, Ci H1 0, psi j, Cj. So if I just had chosen some other basis, which is not an eigen basis of H1, then I would also get shift in the index of the creation annihilation operator. Okay, you can think of it as a scattering. You have some potential, it's one particle, there's an external potential, and the particle scatters from one state to another state. So it's like a scattering element. You know, so the one body term, there's some single particle potential. This is some potential u, and a particle comes in and goes between two states I and j. And the two particle term is you have two particles, I, j, k, l, and they interact with each other, and sometimes you represent them by the exchanging of photon or something. This is some potential V of R really in the approximation we are working in, and that's why all four indices can be different, and similarly, this can also be different. And one of the points of the Hartree-Fock equations is that, in fact, the best basis to choose need not be the phi basis. This is not necessarily the correct basis. You may have to, I mean, and you're kind of familiar with this kind of thing in atomic physics. I mean, in atomic physics, you know, suppose I have a sodium. Sodium is, forget, 21 electrons? No. Anyway, I take an alkali atom, whichever, like sodium. So it's got some, I mean, I forget what the charge of sodium is, 10 or 11 or something. So if I was just thinking in terms of the actual one particle potential, the one particle potential is the nucleus of charge 10. So what would I do? I'd find the single particle eigenstates in a charge 10 nucleus, and I'll get basically hydrogenic wave functions. Okay, but is that a good approximation for the valence electron of sodium, the one that's at the outer shell? Well, it isn't. You know that, in sodium, let's say it has 10 electrons, 9 of them near the core. So if you're very far away, if you're an electron out here, you only see the charge of 1 because there's the nucleus with charge 10 and 9 electrons around it. So you see the charge of 1. So the valence electron far from the nucleus sees a charge of 1. So you want a wave function which looks like hydrogen with charge 1 far from the nucleus, and which close to the nucleus looks like hydrogen with charge 10. So it's a complicated wave function. It's not just the hydrogenic wave function. It's the effective charge it sees is different where you are. So, and that's the effect that the Hartree-Fock equation built in. Okay.
Okay, thank you. Yeah, that clarifies a lot.
All right. Okay, so I think we're done with this chapter now. So now we're going to apply this to the electron gas. I should also say that please do the homework. I mean, I didn't go through a lot of the manipulations in this analysis, and you have to get comfortable with it because these are the tools you're going to be using the rest of the course. So the homework will give you some practice, and that should be on the website soon. Okay, so now let's go to the next chapter, the electron gas. Okay, so this is a very famous problem, which has been intensively studied. But as we'll see, even for this very famous problem, there's still some things that are not fully understood. So this is the problem, sometimes called the jellium model, or more precisely, the electron gas uniform positive background. So what we really want to model is, say an alkali atom like sodium or a crystal, which is an infinite crystal. And the simplest approximation we imagine is that there are these ions, the sodium ions with charge 1, which are just rigidly sitting there. And we are only interested in the valence, the last electron, because that's the one that's going to be really extended through the entire lattice. And going to conduct electricity. We are interested in electrical and heat transport by the electrons. So we just imagine that most of the electrons are tightly bound to the core, and there's this one last electron that's moving around. So that last electron, as it's moving around, from each atom donates one electron to the continuum, to the whole lattice, and the other electrons are bound to the lattice sites. So you have these, so the ions are positive charges. So you have rigid positive charges just sitting there in some lattice. And then, so these are not moving, but then you have some electrons, one for each, the total number of electrons equal to the total number of charges. So everything is neutral. And these electrons are now moving around rapidly everywhere. Okay, so we are interested in these electrons. So the electrons will see a complicated potential. They'll see a potential which has, minima near each positive charge, something like this. It's a periodic potential which looks kind of complicated. And when it gets near the core, you do have to worry about the other electrons and do all the Hartree-Fock analysis to take them to account. And believe me, there are now computer programs that do that in an instant for you. But we want to simplify things just to begin life. And so what we're going to assume is that this background potential, which is highly, which is periodic and varies a lot, and even has a singularity right at each nucleus, if you get really down to the core of the nucleus, we're just going to replace it. So, that understanding this potential is what 295A is about. But in 295B, we're just going to replace that potential by a constant. Okay, so we're going to go from this potential to this potential. So there is nothing there, but it's not as if there's nothing there. There's still, you have to maintain charge neutrality because of the long-range Coulomb force. So there's just a jelly of charge. That's why it's called the jellium model. So you take the positive charge and smooth it out into a jelly of some net. So you have background charge, charge density, rho, which is a constant, which will be equal to the total number of electrons divided by the volume of the system. Because you have to maintain charge neutrality. That's essential. If something is not neutral, it's going to collapse or blow up. Everything has to be globally neutral. That's why this background density You can't just totally ignore it. You need it at various points to stabilize the system. But I will, as we'll see, I won't actually write it down because it's kind of messy to write down what all the terms associated with it. But just keep it in mind that that's there. Okay, so now in this simple jellium model, where we just replaced the complicated crystal by uniform positive background, in this zeroth order model, every metal is the same. Only thing you need to know is the density. So all the properties are fully determined by the density of the background. So in the end, turns out to be only one parameter in the problem, and it's sometimes called RS. It's defined a little bit later, but let me just skip ahead and tell you what RS is. So there's the density, which is N over V or V over N. And then you have some electrons which have a charge and a mass. So now, can you create from the mass of the electron, the charge of the electron, a length? Well, yes, you can. That's called the Bohr radius, h bar squared over me squared. That has a value of 0.5 angstroms or so. And then you can also create, so from the Bohr radius, then you can create a volume. So you can make a sphere of the size of the Bohr radius. That's 4/3 pi a naught cubed. Okay, so however, you have another volume to play with. That's the volume of the system divided by the number of the electrons, which is the inverse density of electrons. Okay, so from these two volumes, you can get a dimensionless number, and that number is called RS. So there's only one number, which and the dimensionality of space that controls everything about this jellium model. And this is the definition of it. This is a dimensionless number. On the left, you have a volume. On the right, you have a volume. And therefore, you can read off RS. So in colloquial term, RS is the radius per particle. So if you imagine each particle was blocking out a sphere, so the amount of volume available per particle is V over N. You make a sphere of that volume, and then you divide the radius of that sphere by the Bohr radius. That gives you the value of RS. So the larger the value of RS, the lower the density. Okay, that's the main thing you got to keep in mind. Okay, so every metal, so to figure out the property of a metal, all I got to tell you is what is RS. And that will depend on the radius of the ions and so on. All I need to tell you, okay, sodium has this RS and potassium has that RS, and they should all be the same, independent. Of course, that's not true. The potential does matter, but let's just, for alkali metals, this is not a bad starting point. Okay. So now we have these electrons moving in this uniform positive background. So there's only two terms fully known for their Hamiltonian in the non-relativistic limit and ignoring spin-orbit interactions. There's the kinetic energy. So now this kinetic energy I've written as in terms of the field operators, which act on R. And I think in one of the homework problems, you'll see how, k squared over 2m, once you go from the plane wave basis to the field operator basis, it's just exactly like this. It's psi diagonal sigma. I have the index sigma to represent the spin of the electron up and down. And psi is a function, it's a field operator that depends on R. So this is just sum on k, h bar squared, k squared over 2m. And here's the Coulomb repulsion. It's the simplest two-body operator we've seen before. Main thing to notice here, oh gosh, have I written this properly? Yeah, so this is the density times the density. Now I haven't normal ordered this, and so you have to keep track of those terms. But all of those terms are basically infinite constants. And they will end up canceling the uniform positive background. But okay. All right, so having written this in real space, let's also write this in momentum space. So we take our system and put it in a box. And And the states we're going to pick, because we have translation invariance, that's the big advantage of the uniform positive background, that almost any type of wave function you pick will be just a plane wave. There's nothing else that's as sensible when you have a uniform positive background. So we pick the functions phi k, which are just plane waves. So now, of course, k is a discrete label, unlike space. And I presume you all know that when you sum over k, that's the same as the volume times the integral in 3 dimensions over 8 pi cubed. Okay. I'll often use this explicit factor of k, and this is normalized to unity, so you have to keep track of these factors of 1 over volume. All right, so you now take this basic interaction, the Coulomb interactions, static Coulomb interaction, and the kinetic energy of the electrons, and you write it out in momentum space. Again, I am not writing out the uniform positive background. We'll see in a minute why I don't really need to keep track of it. It'll take care of itself pretty soon. Okay, so this is the kinetic energy. This makes complete sense. It's diagonal now, so no problem. You just take the number of particles in momentum k and multiply them by h bar squared k squared over 2m. And you sum over spins. Okay, now what is the Fourier transform? So what you get here when you do the compute the matrix elements is you get the Fourier transform of the Coulomb interaction. And in 3 dimensions, the Fourier transform of 1 over x is 4 pi over q squared, where q is the momentum. So this is something you can see if you're from Poisson's equation. Poisson's equation tells you Laplacian squared phi is 4 pi times the density, and you take the Fourier transform, that tells you that the potential is 4 pi density divided by q squared, and that's the 4 pi over q squared. It's the same 4 pi that appears in Laplace's equation, and it just comes to the Fourier transform in 3 dimensions of 1 over x. So if I write this in a pictorial way, this is now very important to write it out and see how all the factors come in, all the indices. So they're written in a very careful way, but we're going to use that a lot. So good to dwell a bit on this structure of this term. So you have 2 particles coming in for momentum k and k prime. So this particle coming with momentum k and momentum sigma. And here you have a particle coming in with momentum k prime and spin sigma prime. So they interact with this Coulomb interaction, and that Coulomb interaction has a momentum transfer of q. Okay, so we have we can say that this Coulomb interaction is transferring momentum this way, in fact, of q. And so there's a factor associated with it. So this picture has a number associated with it. The number, apart from the factor of 1/2 and the 1 over volume that comes from this 1 over square root of volume normalization, is just 4 pi e squared over q squared. So there's a factor with every Coulomb interaction, which is just 4 pi e squared over q squared. And then the particles go out. And what happens? So now you notice it's always in the inverse order. That's really important to get the positive sign in front. So if there's a k prime here, this will be a k prime here, sigma prime, and sigma will match with the first one, and the k with that. But the momentum, so the sigma prime remains the same, sigma prime here and sigma here. This sigma is up or down, but the momentum gets transferred. So k prime, it's as if you can think of it as an electron comes in and it emits momentum q. So just like Kirchhoff's laws. And so you get k prime minus q, and here you absorb momentum q, so you get k plus q. So overall momentum is conserved, and this is the expression for this matrix element. Energy is not conserved. This is just a matrix element, a Hamiltonian. When you actually compute some physical process, you can ask about energy conservation. But momentum conservation is just a consequence of translation invariance of the interaction. The fact that this interaction only depends on x minus x prime. If the interaction depended on something else, some other function of x and x prime, then momentum would not be conserved. Spin is also conserved, well, because the interaction is independent of spin. All right, so this is the picture you should keep in mind, and this is how you write it out explicitly in momentum space. Okay. All right, so now let's do the very simplest thing to this Hamiltonian, which is apply the Hartree-Fock procedure. So now I told you, normally the Hartree-Fock procedure is a huge mess because you don't know which wave functions to use. You have to pick some single particle basis, then figure out the Hartree-Fock Hamiltonian, and then re-diagonalize the Hartree-Fock Hamiltonian. And in general, that's, you have to face that difficulty. But the beautiful thing about the jellium model is that difficulty is not present. And that's one of the important reasons for picking it. In this case, it turns out that the Hartree-Fock wave functions, just like the free electron wave functions, are just plain waves. There is no change between the free wave function and the Hartree-Fock wave function. They're the same. And really, ultimately, what else that had to be the case, because the fact it's a plane wave really relies on nothing more than complete translation invariance of the full Hamiltonian. There is no origin anywhere, no preferred point in either term in the Hamiltonian. Okay, so let's just assume that, and then we can check that that's indeed the case. Okay, so we say that, all right, what we're going to do is we're going to just fill up the lowest energy free particle states. So we're going to take a Fermi sphere here, radius k in momentum space of radius kf, sorry. So that's the Fermi wave vector, and all the states in here are going to be full, and the states outside that are going to be empty. Okay, so the Hartree-Fock wave function then, or our first guess for a wave function is that you just fill up the free particle states inside the Fermi wave vector. And the value of kf is determined by the density that I presume you've seen in 295A or your StatMech course, or that's something you can discuss in the section, the relationship between kf and the density of particles. Okay, and so now the important point is I've got to figure out what my Hartree-Fock Hamiltonian is, and then from that, various other quantities. But the point is the following. So in general, as you'll see here, I have lots of different momenta floating around. And so when I take the expectation value, I could get complicated functions of momenta. So if you take the expectation value of this times this, in general, the results can depend on k and q and k prime in some complicated way. But the important point, and this is something you can already see for this wave function, but is more generally true, that if I look at the expectation value of something like this, c dagger p c q, where p and q are different momenta, let's first do it for this particular state. So if I do it for this particular state, in general, I'll get some function of p and q. But you can easily see that this is actually 0 unless p equals q. And the reason is that, well, these are momentums labeled. These are also momentum labels. So whatever momentum, whatever particle you destroy with q, you better put it back in. Otherwise, the overlap would be 0. So it has to have this delta function. P must equal q. And then the rest, n of p, which is the number of particle momentum p, when p equals q, that can be some strange function of p in general. Okay. So, and you can see that this is actually a more general statement, not just for this particular wave function. As long as this wave function is translationally invariant, looks the same as you change the origin of coordinates, then this this operator also better be translation invariant, otherwise the expectation value would be 0. And the only combination with translation invariant is when the momenta are the same. Okay. But that's the more general group theoretical type reasoning, done kind of sloppily. But all right. Okay. So because of this, so you always get delta PQ. So what this means, if I go back to the previous chapter, I have the A dagger, B dagger, C dagger, D, when I was doing something like this, let me just work it out. Let me take this object here. You see how it works. So let's see if I can even remember this. C dagger, let me not write on all the spin, K plus Q, C dagger, K prime minus Q, C K prime, C K. Okay, so now suppose I'm going to take the expectation value of these two. So if I take the expectation value of these two, now these two momenta have to equal. So this tells me that Q equals 0. And lo and behold, that is also diagonal in K then. And similarly with the others, you can see that no matter what happens, the Hamiltonian in the end would be diagonal in K, which tells me that the eigenstates of the Hamiltonian are plane waves. So I'm done. So the eigenstates of the Hartree-Fock Hamiltonian, which I will write down explicitly in a bit, I can already see, even without writing out explicitly, that its eigenstates are plane waves. So I'm done. So everything is, I have my exact Hartree-Fock wave function. You give me the density of particles, and I give you the wave function. There's nothing else. Okay, and that is, I'm guaranteed to solve the Hartree-Fock equations, at least for the jellium model, by this simple procedure. I should say, if you had a more complicated potential with, the whole thing, the whole shebang, then the problem is not that simple at all. You do have to do a lot of number crunching to get it right. Okay, so now let's just look at the expectation value of the true Hamiltonian. So the first term is just the expectation of the kinetic energy. So you just take the kinetic energies of all the particles inside the Fermi sphere. All right, and now you take the Coulomb term and you look at the expectation value of this term here. And remember, now all we're doing is applying our rule. That's the expectation value of A dagger B, A dagger B dagger C D is just expectation value of A dagger D times B dagger C minus expectation value of A dagger C times B dagger D. So we're just applying that rule. So first, let's take the first term. So the first term, so we just apply it. Okay. Well, so what happens? Well, you look at the expectation value of this term right here, and also this one, and this tells you right away that you have a problem. So this is only non-zero when Q is 0. It has to conserve momentum. This is only so we have to put Q equals 0. And the same over here. But Q equals 0 is an infinity out there. Okay. So what we are finding is that somehow the whole thing is blowing up. But this is where the uniform positive background comes to rescue us, because just think about what we're doing. When we take the expectation value and replace it by constant, we're just assuming that the electron density is a constant. We have these electrons moving in this Hartree-Fock wave function. We're just computing its density. So we've got a term here, which is just the density of electrons, which is independent of position. So it's some number, some negative number, which is the density of electrons here. And the other term is also the density of electrons. So we are accounting for the repulsion between the electrons. And it is true, if you just had electrons, which are uniform density, they have a repulsive energy that's not thermal, it's even larger than the volume, and the whole thing will blow up. But of course, we have this positive background. So we have taken our electrons, we have taken our electrons and smeared them out into their own jelly in this Hartree-Fock approximation. The electrons are totally smeared out in a jelly, as are the positive charges. And now, of course, however, we know that the positive density has to be exactly equal and opposite to the negative density. So if I'm sitting somewhere at any point and I've smeared out the electrons and I've smeared out the ions, the net density at that point is 0. There is nothing. So all the terms that I didn't write out associated with uniform positive background, this is the only place they rear their head. And they just tell me, replace this infinity by 0. That's it, because the smooth density of electron just canceled by the smooth density of the ions. The point is, of course, the smooth density of ions is just classically just sitting there. The electrons are not smooth. They're quantum particles with a complicated wave function. But we've just found one term in the Hartree-Fock analysis, which just only depends on their density. Okay. So this term is 0. So the term that's looked to be positive in infinity is actually 0. All right, but there's another term, there's this term here. What about this term? That term has a negative sign. So we are going to find that the Coulomb interaction gives you a negative contribution to the energy, not positive. And that's a purely quantum effect. So I take the other term, A dagger, whatever, A dagger C, B dagger D. So this is the expectation value here. Okay, and now these momenta have to add up to 0. So now Q is not 0, Q is equal to K prime minus K. Okay, so now I deduce that Q, this tells me that Q is equal to K prime minus K. Both terms tell me the same thing, fortunately. This tells me Q equals, has to by momentum conservation. For this momenta to equal that, Q is K prime minus K, and then similarly here. Not just that, there's a factor of the spin initially could be different. Sigma and sigma prime are 2 different spins. Now they have to be the same. Otherwise, this is 0. Okay, so the factor of 1/2 doesn't disappear because the spin, factor of 1/2 is also there, but there's the sum over sigma, which I haven't written down here, the sum over sigma and sigma prime will only give you a factor of 2, not a factor of 4, as you might have initially thought. Okay, so all right, so now you've, worked this out. And now what happens? Sorry, I've totally forgotten here. Okay. Okay, so so Q equals K prime minus K. So that Q equals, yes. Okay, that gives you this. And then what else? So there you have some constraints. So for this to be non-zero, you have to annihilate a particle that's already there. So K prime has to be less than the Fermi wave vector, and K has to be less than the Fermi wave vector. And then you have to sum over K and K prime. And so this is what you get. Okay. And then there's a sum over sigma that cancels the factor of 2. Okay. And this is just some integral. And let me write out this integral for your benefit. That's, it's 4 pi e squared over v. And then there's v squared times d3k, d3k prime over 2 pi to the power 6. And then times 1 over k minus k prime squared, and this goes from 0 to kf. So sum over occupied states with 1 over k minus k prime squared. Okay, so that's a complicated integral, but it can be done. It's just a number. Okay, so then this is where you introduce all these dimensionless units. You write everything, the energy per particle. So there's the energy per particle in the jellium model. And the full answer of Hartree-Fock theory are these two terms. This is the kinetic energy term, which ends up going as 1 over Rs squared. And this is the potential energy term, which is negative and goes as 1 over Rs. Now I put dot here because it turns out these two terms, even though they were obtained in a Hartree-Fock calculation, are the exact results in a series in small rs. So if you make a series in 1 over, large rs, sorry. So this term is the largest term when rs, sorry, I always forget it. It's a series in small rs, sorry. So this is 1 over rs squared, this is 1 over rs, the next term will be order 1, then rs squared. It's not as simple as that. There are non-analytic powers of rs with logs and so on. But these are the leading terms in a small rs expansion, in addition to being the variational estimate at all energies using the Hartree-Fock approach. Okay, I'm out of time. So let me just finally try to explain the negative sign. Why is it quantum effects give you a negative sign? Anybody have a guess? So keep in mind, this negative sign comes entirely from electrons with the same spin. So just think about what's the difference between electrons with the same spin as opposed to the opposite spin. Well, electrons with the same spin obey the exclusion principle. They can't be at the same point. Electrons with the opposite spin can go right through each other. So electrons with the, so when you form a Fermi sea of electrons, that Fermi sea obeys the Pauli exclusion principle for all spin-up particles. And so on the average, spin-up particles, because of the exclusion effect, are farther apart from each other than they would be in a classical gas. They stay away from each other because the wave function vanishes when they approach each other. The Slater determinant is not a trivial, it's not a constant. Slater determinant is building up some very subtle correlations between the particles so that when they get next to each other, the wave function vanishes. And it's only building that up for spin-up particles with other spin-up particles. So there is a correlation, quantum correlation from the Fermi statistics that's keeping the particles apart. And so there are, so on average, two spin-up particles are farther apart than they would be in a classical gas. And since the interaction between them is repulsive, you gain some energy. Okay, so spin-up particles gain energy. And in the end, that is also the effect that comes entirely from the Fock term. You notice this is the Fock term where you exchange the particles. And that's also the physics behind ferromagnetism. So if you make all the particles spin up in a ferromagnet, well, they will stay apart from each other and so lower the energy. On the other hand, so why isn't everything ferromagnetic? Well, if you made all the particles spin up, the Fermi wave vector become much larger and you'd pay a much higher cost in the kinetic energy. So for something like sodium, the kinetic energy wins. And for something like iron, this term wins. That has to do with the more complicated details of the band structure. And it's this kind of term, or this exchange energy, sometimes called that, or this coming from the exclusion principle that leads to magnetism in some cases, but for the uniform electron gas, it's just a negative correction to the ground state energy at small rs. Okay. Any questions?
Yeah, I have a question about how this energy is computed by experimentalists.
Experimentalists?
Yeah, like, is it
no,
possible?
I don't know if they can. Well, first of all, experimentalists measure things, but
yeah,
these days they also compute things. No, this is
Yes.
just one term in the total energy. But I think the way to think about it is, okay, an experimentalist could have, you could have some material in which one state is ferromagnetic and the other state is not, and if you could somehow measure the free energy difference, that free energy difference of the ferromagnetic versus the non-ferromagnetic state would have, some contribution from this term. Okay, because this term would be absent in the fully ferromagnetic state. Sorry, it would be absent. No, it'd be present in both states. It'd be much larger in the ferromagnetic state than in the non-ferromagnetic state. Yeah, it's not totally absent. Now, of course, this is not the full story. Of course, there's the ... And to get the ... you have to do much better. You have to put in exchange correlation effects that density functional does using results from quantum Monte Carlo. Then you have to put the effect of the potential, and that also density functional theory does. And now you can download various packages on the internet where all you need to do is just tell where the ions are, and it'll compute all the terms for you using a more sophisticated version of the theory that I've just presented. But the common feature of all these theories is that the starting point is that you assume the wave function is a Slater determinant with some corrections, small corrections. I mean, Hartree-Fock theory, there are no corrections. In density functional theory, there are corrections, but they're assumed to be under perturbative control. Okay, any other questions? All right, and just a reminder, I'm going to continue the discussion sessions at 9 p.m. Let's see how they work. 9 p.m. on Friday night, I don't know, but you never know in the pandemic. Any time is as good as any other time, I presume. All right, and the homework should be up later this afternoon, so please look at it over the weekend. All right, see you soon.
Thank you.